Jack Dongarra, Professor Jack Dongarra from University of Tennessee, Quelles National Laboratory and the University of Manchester, will give the first talk. So he will speak and give an overview on high-performance computing and challenges for the future.
Thanks very much, Serge. It's a pleasure to be here. I don't think I've ever given a talk in the shadow of such an elegant structure to our left here. So I'm going to talk about high-performance computing and look at some of the issues that we have to face in the future. Just as an overview with that. And I'll have to say that as we move towards exascale, moving towards extreme computing, some of the... Talk to the microphone. Is that better? Okay. Yes. I'll take whatever I'm given. Okay, very good. So I can wander around. Okay, so we're going to look at high performance computing. But first, what I want to do is to look at HPC through the eyes of some data that we've collected. So this is the data that's called the top 500. It's a set of data that's been around for almost 25 years. So this is something that started with Hans Moyer, Eric Strohmeyer, and myself, and then later Horst Simon joined the group. And the idea here is to produce a list of the 500 fastest computers. And we're going to do that using some metric, and the metric is the LIMPAC benchmark. And we can argue if that's a good or a bad thing, but that's the data that we have. So picture this. The rules for this benchmark say you must implement Gaussian elimination with partial pivoting. So that's the algorithm. You must do that. And I'm going to give you a matrix, and you're going to solve that as best you can, optimizing the code for Gaussian elimination with partial pivoting on a large matrix. I give you the matrix, but you can make it as big as you'd like. And then we're going to check to see if you get the right answer. And everything is checked with 64-bit floating point arithmetic. So that's sort of the ground rules. And we're going to solve that problem, AX equal B, a dense matrix problem, again, this benchmark started almost 40 years ago. So 40 years ago is when this was created. This goes back a long time. And computers were quite different 40 years ago than they are today. This benchmark maybe was relevant 40 years ago. Today there's a big question mark how relevant it is. But this is what we have. So this, in some sense, is a snapshot of high-performance computing dating back to 1993 to today. And the way to read this is, this red line here charts the number one computer. So the number one computer is at 93 petaflops, 93 times 10 to the 15 floating point operations per second. And again, that's double precision, and by operations I mean adds and multiplies. So that's what's being measured here. So that's the fastest computer on the list today, number one, and this is number 500, 432 teraflops. So that's the machine that just made it on the list. So if we think about those 500 computers as being called supercomputers, your machine, if you have a computer and you want to be called a supercomputer, you have to be somewhere between that range. And the blue line represents the sum of the computers. That's an Excel sheet computation. That's the artificial number there. The other ones are actually running the benchmark, getting the results. So we can see where things have been. You see jumps that occur occasionally when a new machine comes in, which is much greater than the previous machine. And this line is more or less straight, as is the blue line. There's something going on here. There's a bit of a deflection there. Maybe that's because the economy turned down, or maybe because Moore's law is slowing down. Something's going on there. We haven't quite got a handle on it. Okay, so the guy at the bottom of the list today, that was equal to the sum of all the computers back in 2001. So things change quite rapidly, right? This is exponential, and that's what happens when you're on an exponential curve. The thing to realize is that a supercomputer, after 6 years, is no longer considered a supercomputer. In fact, it falls off the list. So the guys at number one position cost roughly 200 million US dollars. So that's the investment that's made. And after 6 years, it's not even considered a supercomputer. So an investment, if you're going to be in this business, you have to do that investment every 3 or 4 years to stay on track with those computers. So it's a big enterprise. You know, the technology technology changes incredibly fast. So my laptop, this is a Intel, it's a quad-core Intel processor inside my laptop. I can run the benchmark on my laptop. And when I run the benchmark, I get 166 gigaflops. You know, that's stunning. This is a computer I use to read email. And I get a lot of email, but you know that performance there is just incredible in terms of what the capability is. My laptop was faster than the #1 machine back in 1996, and that's a Fujitsu wind tunnel. Just to put that in perspective, the #1 machine with 60 gigaflops was a Thinking Machine CM5 with 1,000 processors. So this device here is much faster than that computer at Los Alamos used to carry out nuclear weapons computations. So incredible changes taking place in a relatively short period of time. Okay, so this is looking at that list and extrapolating a bit. So we've got the same set of points here, and now we're going to go out a little bit further to understand where things are. The thing to realize here, we reached a teraflop. The first computer that hit a teraflop was back in 1997, and that was at Sandia National Laboratory. It was called the ASCII Red computer. That's the first teraflop computer. About 11 years later, there was a machine at Los Alamos, and that was the first computer to reach a petaflop. 10 to the 15 operations per second. And the projection says, you know, we could get to an exaflop in the year 2020. So an exaflop computer in the year 2020. China says they're going to be there. So China's already said, they put a stake in the ground and say, we're going to get to exaflop, we're going to build an exaflop computer, and we'll put it in place in the year 2020. In the US, the statement from the Department of Energy is 2021. So it's a year after the Chinese get their machine on the ground. You know, the technology changes very rapidly. Today we have chips. This is Intel's Knights Landing, and this is a Shenwei processor, the guy that's in the #1 computer today. Those chips have a peak performance of 3 teraflops. So that's essentially what we were achieving with that machine back in 1997. And one rack of that Tianhe Light computer is about 3 petaflops, and that's the whole Roadrunner computer at Los Alamos. So again, things are changing quite rapidly on this exponential curve. Here's sort of the state of high-performance computing today. If we look at that list of the top 500 computers today, there's 138 systems which have greater than a petaflop performance, right, out of the 500 computers. And we see 3 technologies that are there for high-performance computing. One technology is just to put Intel processors, commodity processors in a box and connect them together with some fast interconnect, maybe InfiniBand. The second architecture that's there is using commodity processors again with an accelerator. Think NVIDIA. So you put a large number of Intel processors tied together with a co-processor to do floating point to accelerate the computation.
It was there a few weeks ago. What do you think about the Matrix 2000 accelerator that China developed?
So Serge is referring to a computer that was built by the National University for Defense Technology. They had a computer called the Tianhe 2, I mentioned this embargo against Intel giving parts. The Tianhe 2 was to be upgraded using Knights Landing. Because of the embargo, they could not use the next generation of Intel parts, and the result of that was they built their own. So they have their own accelerator called the Matrix 2000. It produces roughly the same performance as a Knights Landing processor, 3 teraflops, and you know, it's all about software. So you know, one of the critical issues here is building that software stack for that processor, and can they do that, and can they optimize it so they can really extract the 3 teraflops of performance. So that's a question that still has to be resolved. So we don't know the answer to that. But it does show that there's an investment being made. They're developing their own technology. The #1 computer, the Shenwei processor, that's a water-cooled machine, and today they're producing a air-cooled version of that. And that air-cooled version is going to be sold in China as a rack that'll be used for their weather. The Meteo in China will be using that computer to do some of their calculations. So I think there's an intent there to push that out. How far that gets pushed out is something that's to be seen. Any other questions before we strive for?
You said that you need to have the software layers, but I expect they already do computation on these procedures.
Absolutely. So the question is, how efficiently can they do those computations?
And did you check that? You have any way?
So they're putting in place today the LINPACK benchmark, the top 500 number for their new computer. The numbers that I've seen are a little disappointing in terms of the percent of peak from that, and that's characteristic of a new architecture where you have to optimize the code. So I think they will increase, things will get better, but today it's not at that point. Well, the projector is very slow in coming on.
What do you think about the processor of the number one? So we discussed yesterday. You have 4 crossbar connect with internship network. So that means that perhaps in the future, even one processor will not have any shared memory, and you will have to have some connection between different parts of the.
So the Chinese processor that's in the number one computer is a processor. It's a chip which has 260 cores. 260 cores. That chip is composed of 4 modules. Each of those modules contains a master process plus a 8x8 grid of worker processes. So there are 4 of those things replicated in that configuration. And the way to think of that chip is that there are 4 MPI processes for each of the 4 quadrants of that chip, and then the worker sends off things to the 8x8 grid as an accelerator, and they use OpenCL to do that. So that's again a mechanism for extracting performance. It's a different design point for an architecture, but that architecture was designed specifically for high performance computing. It wasn't designed to run Windows, it wasn't designed for databases, it wasn't designed for deep learning. It was designed for high performance computing. And that's their design point. That's where they decided to target. And that chip in that computer is being used today at scale to solve real problems. And just to put that in context, we have in high performance computing we have this prize called the Gordon Bell Prize. The Gordon Bell Prize is awarded to the best implementation of an application that beats previous year's applications. And this is done at the SC conference. Gordon Bell is this architect, legendary architect. He designed systems. He worked at Digital and designed the DEC VAX computer and designed all sorts of other machines since then. So he decided to fund this prize. So he gives away $10,000 a year to the winner. $10,000 every year to the winner. Last year, and the way this works is, if you want to compete, you write a paper describing your application run on a supercomputer and why and how you did it that's better than anything that was done before. So that's the mechanism. You submit that paper to supercomputing. There's a committee which looks at these papers and then evaluates them and selects at most 6 papers for the competition. And those papers then get refined, and then the committee decides on the winner, and then that guy gets $10,000. Last year at SC, there were 6 papers, and 3 of those papers came from China, running on the Tianhu Light, running on the number one computer. And the winner was one of those. So again, it was 10 million cores at scale doing an atmospheric climate modeling problem. So that, so the question really might be, is it a stunt machine? Is it designed just to do LINPACK very fast? And I would say, you know, based on the results of that, that work, it's not just a stunt machine. They're able to do real applications. This year at supercomputing, there were only 3 papers that made it into the final. 3 papers, not 6, 3 papers. 2 of those are coming from China, running on the Tianhe Light. The other one is a group from Princeton and Microsoft doing something on a high-performance computing system. So I think there is something there with that architecture. It's good in terms of competition. How effective that's going to be in the end, we'll have to wait and see. China has 3 projects right now competing for exascale. These are prototype systems. And they're competing in the sense that they have funding to develop a machine that's an example of what the exascale machine might be. So one machine is a follow-on to the number 1 machine, the Tianhe Light. Another project is a follow-on to the number 2 machine, the Tianhe 2A. And the third one is a computer from a company called Sugun, a Chinese company that builds x86 products. And that company, Sugun, has a license for the x86 architecture. And the result of that is going to be a big machine that they hope to reach exascale.
So they are the main power failure, so you can take 5 or 10 minutes to reboot. So I think I will keep this.
Sure, yeah, okay, let's do that.
So I know that after in your talk you explained that perhaps the impact test is not really adapted for now, and that you discuss about the conjugate gradient benchmark.
Right.
So the performance, the efficiency is lower. So you said that Gordon Bell or this kind of price in supercomputing. So how is the performance of this select project or supercomputing compared to the benchmark of the conjugate gradient?
I see light. There is a hope, as they say.
It's the first time we have to share that with.
Okay. So back to the story here. Okay, so we've seen these architectures and so on. Intel has this incredible situation. 92% of the 500 computers. AMD has another 1%. I think that's really stunning. This is a graph of the 500 computers. So there are 500 rectangles here. Each rectangle represents a supercomputer on the list. The area of the rectangle represents the power of that supercomputer. So that's the number 1 computer right there. And they're color-coded in terms of where they come from. So China has the number 1 computer, the number 2 computer. This is Switzerland. It has the number 3 computer. The number 4 computer is somewhere over here in the US. So, you know, here's an interesting set of numbers here. The US has 168 machines on the top 500 list. That's the lowest number that the US has ever had, 168 machines. China has 160 machines on the list, 160 machines. So that's a pretty high number for China. In 2001, they had 0 computers on the list. So you can see the investment that's been made in a very short time in terms of high-performance computing. You see there that Japan has 33, Germany 28, and France has 18 machines on the list. And again, this is China has roughly 1/3 of the systems, and the U.S. has come to this point. So this is a list of the top 10 computers. So the way to read this is that's number 1. It's at the National Supercomputing Center in Wuxi. It's called the Sunway Tianhe Light. It uses this processor. That's the Shenwei 2610 processor, 260 cores. It has a custom interconnect, so they put their own interconnect in it. So they built their own processor, they built their own interconnect, they're using their own operating operating system. They built their own software stack, and they're using a lot of open source software in their applications. That's in China. It has 10 million cores. 10 million cores. So if you're going to program this thing at scale, you have to manage 10 million threads of execution. And for the benchmark, they achieved 93 petaflops. That was actually running the benchmark, and that's 74% of the theoretical peak performance. The theoretical peak is a paper and pencil calculation. What's the cycle time? How many operations per cycle? How many cores do you have? And that's how you get the theoretical peak. The machine uses 15 megawatts under load, so that's the power that it's consuming under load, 15 megawatts, and that's for the memory, the CPU, and the interconnect. It does not include the cooling of the machine. Cooling's another 30%. So in the US, 1 megawatt year will cost $1 million. So I have a computer that's 1 megawatt, and I run it for 1 year. I'm going to get a bill from the electric company for $1 million. So $15 million is the power bill to turn that machine on, basically. I don't know what it is here in France or in Europe, but it's probably Europe. Sorry?
€1 million.
1 million euro, close enough. Right, that's right. And this is an efficiency number, gigaflops per watt. So you want that number to be as high as possible. So they're at 6 gigaflops per watt, which is not bad. 6 gigaflops per watt. If you look down the list here, the only one that beats it is the machine in Switzerland, the Pizdans, which uses NVIDIA accelerators to do its business. So we've got a couple machines in China, 5 in the US, 1 in Switzerland, and 2 in Japan in the top 10 list. Again, US is number 4 in this list. That's probably the first time it's not in the upper end of that list. This machine here is incredibly powerful, right? Incredibly powerful. It requires, if you were to add up the next 5 machines, you would get to that 1 machine. So if you connected together somehow those 5 machines, that's equivalent to that 1 computer. That's a big computer that they have. And if you take the sum of all the machines in the EU, the sum of all the machines, including Switzerland, the Tahoe Light is equivalent to 60% of that. So again, a very large machine. In the US, if you take all the machines on the top 500 list, it's about a third of all the machines in the US. So that's an incredible, powerful machine. And much greater, so it's a big machine. So it's based on this processor. This is the Shenwei processor. It was produced, they claim, in the Shanghai High Performance Computing Center. It was done by the National Science and Technology Place. It uses 28 nanometer technology. Just to put that in context, Intel's Knights Landing is 14 nanometers. So this is using slightly older technology. 260 cores, 3 teraflops is the peak performance for that chip. And the way this machine is built, this is the chip, and again, there's these 4 quadrants on the chip. There's a master process, and then 64 of these 8x8 grid of worker processes. They're connected by some interconnect on the chip, and this master process is a heavyweight process. It has cache. The lightweight processors don't have any cache. They have a scratch pad memory. And they do computations through that scratch pad. One cabinet of the machine has 1,000 of those chips in it, and each chip is considered a node. And the whole system is about 40 cabinets, and it takes about the size of this room here, maybe a little bit bigger than this room for that. This machine is running at 1.45 gigahertz, so relatively slow cycle time. It uses DDR3 memory, last generation memory as well, so rather slow memory associated with it. And that's how they get the power budget down. So using very slow clock and slow memory associated with it. They have a lot of it in the system. And again, they're able to get this 6 gigaflops per watt. The machine is water cooled, and they're often running with that configuration. And they claim the machine cost $280 million US dollars to put that in place. Okay, so this is the story about the Gordon Bell thing. I think I've already described it. I'm going to skip over this. Again, Gordon Bell has this way of prize. These are the 6 entries from last year's Gordon Bell Prize contestants. These are the 3 that are from China, and this last one here is the one that actually won the prize. Running at scale, running on that machine. This year, these are the 3 that have made the cut in terms of being contestants for the Gordon Bell Prize. We don't know who the winner is yet. That'll happen at supercomputing, but those are the 3 there. So these 2, the top 2 have been done at using the Chinese computer. So is it a stun computer? I would say it's not a stun computer. It's being used to do real science here. It seems to be quite active. They're willing, if you wanted an account on this machine, you can subscribe and they would give you an account on the machine. Again, China has these 3 projects going towards exascale, so these are all contenders to build an exascale machine. They're going to upgrade this machine here and make it even faster. They're going to upgrade this machine with this accelerator, and then these guys at Sugan are this x86-based architecture that they hope to push out. In the U.S., the exascale plan is a plan which started last year. It's a 7-year plan. They plan to put in place an exascale machine in the year 2021, and that'll be followed by a couple of other machines a year or 2 after that. And in the U.S., exascale is being defined in terms of these quantities. So it's exascale computer is going to be 50 times the performance of today's 20 petaflop system. It has to have a power budget somewhere between 20 and 30 megawatts. They want to be able to have 1 perceived fault per week. I find that an incredible challenge. One fault per week in the machine. And they're going to have software, of course, to support a wide range of applications. In the U.S., the next 2 big machines that are going to be put in place are coming next year. They're actually starting right now. There's a machine at Oak Ridge National Laboratory that's being put in place, and also at Lawrence Livermore National Laboratory. Those are IBM systems, IBM Power 9, with NVIDIA Volta processors, accelerators on those machines. And those machines will be somewhere around 200, maybe a little bit higher petaflops systems. So large machines. They're being deployed now. They plan to have a fully configured machine in next summer of 2018. And after that, in 2021, the plan is to put in place an exascale system, and that system will be given to Argonne National Laboratory. It's being designed now. They don't have a design yet. It's going to be Intel-based. So Intel, with some future generation processor, will be placed in there. It's going to be balanced architecture. It's going to be able to do the traditional things that we think about using supercomputers for, but also doing things like deep learning. So we'll have some capability for doing perhaps short precision. So deep learning can be driven by 16-bit floating point. So you want to have hardware that does 16-bit floating point very rapidly. So there's a standard for that, and some vendors actually have hardware in place for doing 16-bit floating point. NVIDIA does, as well as Intel and AMD. So this is the DOE plans. It's an integrated plan. It's going to have applications, software technology, hardware, and ultimately exascale systems. It's being developed today. It's a plan which is roughly on the order of $1 billion per year. $1 billion per year is going into it. So IDC, they're now called Hybrid Research, did a study last year, and this is what they came up with. They said in the U.S., there's a $1 to $2 billion a year investment in high-performance computing leading to exascale. In the EU, there's about a $5 billion in total being spent for exascale, pre-exascale systems. China is investing about $1 billion a year for exascale things, and Japan has in place a mechanism for getting to the next generation of machines on the order of $1 billion over 5 years. So that's a study that came from IDC last year. Okay, we touched on this LINPACK business. LINPACK, for my sins, I'm an accidental benchmarker, right? This is not something that was I set out to do. 40 years ago, as a side in developing some software, I put together a list of the computers that ran that software. That software was called LINPACK, and that list has taken on a life of its own. So 40 years ago, or 20 years ago, maybe it was a good way to measure the performance of computers, but today it isn't. This benchmark is driven by matrix multiply. So if your application is driven by multiplying two matrices together, then this is a good benchmark for you. But most applications are not. In the old days, floating point was expensive. Today, floating point is over-provisioned in our hardware. We have an excess of floating point, and that's not the problem. The problem is in moving data, and data movement is the thing that really kills the performance. So the benchmark that we have should better reflect that characteristic. What we'd like to do is to point out a weakness in a machine and then have vendors address that weakness. This benchmark doesn't do that. This benchmark, the LINPACK benchmark, looks only at floating point performance, and they've done an excellent job of providing that. So today's applications, the applications that we would see on large Department of Energy computers in the US are driven by this kind of computation. They're solving a three-dimensional partial differential equation. They discretize that differential equation, and then they solve that, they approximate the solution using a sparse system of linear equations that has to be solved in getting the approximate solution to that PDE. So solving a sparse matrix problem is the thing that really is driving much of the computations that we see, at least in the Department of Energy. So the Department of Energy said to us, maybe you should invest in a benchmark that does that. So we did a study and came up with this benchmark. So this benchmark here looks at solving the sparse matrix problem using a conjugate gradient method. There's a large sparse matrix. It comes from a three-dimensional problem. There's a 27-point stencil resulting in a matrix problem which is sparse that can be solved using some iterative solver. So iterative solvers have data motion, a lot of data movement, and not a lot of floating point arithmetic compared to the data movement. So that's the thing that's going to be stressed in this benchmark. And those two benchmarks perhaps provide a bookend to your computer's performance. At the high end is the LINPACK benchmark, and at the low end is something called HPCG. So this is a comparison. This is a list of the top 10 computers running that benchmark, HPCG. So what do we see? The number one computer is the K computer at RECAN. That's a computer that's been in place for a while. It was designed for high-performance computing. So this was not designed to do databases or Word or anything else like that. It's designed really for scientific computing. It has 700,000 cores. It achieved, with LINPACK, 10 petaflops. For HPCG, it gets 0.6 petaflops. So that's the spread, if you will, between doing matrix multiply and doing something on a sparse matrix. So that's 5.3% of the theoretical peak performance of that machine, 5.3%. And if you take a look down the list here, you see a number of machines which perhaps did very well on LINPACK, like this machine from the number one machine on the LINPACK benchmark. It receives 0.4% of the theoretical peak. 0.4% of theoretical peak. That's an incredibly low number, right? So data movement is killing the performance here. It's all about data movement for this benchmark. This machine doesn't do very well in terms of data movement compared to floating point. So it suffers from that. So many applications, when run on this machine, would probably end up with this kind of effect in terms of the theoretical peak performance of the machines that we see. And low numbers are common. 5 is very good, 5% of theoretical peak. Again, that's probably a low number, but the other numbers are somewhere between 1 and 2% of the theoretical peak of those machines. So if you take a look at the benchmark results, this is the blue line here is charting the LINPACK. The blue line is charting the peak performance. The red line is charting the number that comes from the LINPACK benchmark. That would be the number that's used for the top 500. And HPCG is this green line here. So that's the spread, roughly. You're looking at 3 orders of magnitude difference between what we see from running that close to peak performance and what we see for perhaps a real application on this machine. Well, I must be coming close to the end of my time. No, I'm not. I'm okay. Okay, I'll take as much time as I need. Okay, good. not that much time. Okay. And so as we go towards extreme computing, there's a number of issues that we have to look at. One issue is issues relating to Moore's law and Dennard scaling. So Moore's law is this incredible curve that we've been on, right? This is we know the story very well. You look at the processors that Intel has provided over the course of the years, and the number of transistor has been increasing at that incredible rate. And it doesn't apply just to processors. If we take a look at things like hard drives, so we get this image of a 5 megabyte hard drive which weighed a few tons back in 1956, and today we get a half a terabyte on something which is about the size of our fingernail, which is an incredible change that's taken place over that very short period of time. Dennard scaling, though, is the real secret sauce to Moore's law. So Moore's law gives us transistors, but Dennard is the guy who said, look, here's the situation we're in with the electronics that we have today. It's a fact that with Dennard scaling, we could decrease the feature size by some factor, and that results in a decreasing the voltage by that factor, and it says the transistor count can be increased by that factor squared. Those are incredible situations. Not only that, the clock speed can also be increased by that factor. So in the old days, Dennard scaling was the thing that made my processor in my new computer run my applications a lot faster with me not having to do anything. I get a new computer, I got a new processor in that computer, I take my application and run it. Dennard scaling was in control, and it said things are going to run faster by some magical process there. Unfortunately, so we get this effect of 2 times the transistor count, 40% faster and 50% more efficient. That's an incredible situation we were in. Unfortunately, Dennard scaling ended around 2004, and that was the result of, with things getting smaller, voltage leakage, and the result of that voltage leakage was things heating up, and we couldn't maintain that increase in terms of the clock scaling in the presence of those conditions. So things today are sort of frozen around 3 gigahertz, and that's a result of Dennard scaling. Moore's law continues, and those transistors that appear here increasing at that rate get put in place in terms of more cores on the chip. So we end up with many-core, multi-core and many-core on our processors with the cycle time roughly around 3 gigahertz, with Dennard scaling really ending at that point, unfortunately. Data movement is very expensive compared to floating point performance. If you take a look at what Intel has done with their chips, this is sort of a little history here of Intel processors, going back to Xeon processors in 2009. Each core at that point did 4 floating point operations per cycle. So that's what happened in 2009. The next generation gave us 8 floating point operations per cycle per core. Haswell processors, you got 16 floating point operations per cycle per core. Here's where we are today, Skylake and also Knight's Landing. They provide 32 floating point operations per cycle per core. That's an incredible rate of execution. Knight's Landing has 68 cores. Each of those can be driven at that rate. That's incredible. Over provision for floating point. We have tremendous floating point capability. We can't get the data there. And the result of that is the application's running at 3% of theoretical peak. So that's the situation we have today. Perhaps that's the result of the LINPACK benchmark driving matrix multiply, encouraging hardware to be invested in that approach of giving us floating point capability, but not really addressing the data movement issues. So that I find is an incredible thing. You take a look at data movement, the number of cycles to get data from memory, DDR4 memory, is about 180 cycles. So it takes 180 cycles to make that request from memory and get that here. Remember, in 180 cycles, I'm doing 32 flops per cycle per core. So I've got all this tremendous capability that's being wasted in some sense because I'm waiting for my data to arrive. And you can see that also in terms of the energy budget. The energy budget here for floating point operations is about 20 picojoules. The energy for moving data from memory is about 16,000 picojoules. So again, it's an expense that has to be paid for. Power is a big deal in terms of our computing, and we're spending a lot of that just moving data around in our systems. The other issue that we have is we have all this parallelism that we have in place. And the memory storage really is not keeping pace with the floating point rate. So if I take a look at machines that have come to us at Oak Ridge National Laboratory, we have 3 generations of machines, Jaguar, Titan, and soon to be called Summit. If you take a look at the memory per floating point, we see a big change as those machines are being put in place. A big change in terms of less memory given the floating point capability of those machines. And that's going to be a big issue. Stack memory is here to help mitigate that to some level. So Knight's Landing has these 4 layers of memory that are stacked, allowing for greater bandwidth through that stack to the processor. So the Knight's Landing chip actually has up to 16 gigabytes of memory sitting right next to it on that substrate. And let's see, this is about our friends at NVIDIA looking at floating point execution. We have 64-bit floating point rates, we have 32-bit floating point rates, and today they're giving us something that they call tensor cores, and those are really doing 16-bit floating point arithmetic. 16-bit floating point arithmetic is big for deep learning, and they're developing hardware that runs at 120 teraflops out of that accelerator. The 16-bit floating point arithmetic has some limitations. 16-bit floating point arithmetic says the largest number you can have is 64,000. Any number that's bigger than that would overflow. So we have to take pretty extreme measures if we're going to be using that for our normal scientific computing. And this is a chart here that's supposed to illustrate that effect with our 3 machines at Oak Ridge. This is Jaguar. The ratio of memory to floating point capability was at 0.1. With our current machine Titan, it's at 0.03, and the new machine Summit, it's going to be at 0.01. So you see that big change there in terms of the amount of memory that's in the machine and the floating point rates. So that has an implication on the size of the problem that you can solve on these bigger machines. We don't have enough memory here to really adequately address that, is one concern. Another issue with high-performance computing is clock variation. So we think about writing a loop and having that loop run in parallel, perhaps. So we think about we launch something, it's going to run in parallel, and what we would expect to happen is for everything to be finished at roughly the same time. If it's finished at the same time, then we minimize the synchronization, and we can go on and do something after that. Clock jitter, the variation that we have in the processors today, provide us with a rather unusual situation. Our processors can exhibit something called turbo boost. Turbo boost is something that happens in the hardware on Intel processors. It happens without my control. It says I can run the process faster if certain conditions are present. Or perhaps if the processor is heating up, it'll turn down the cycle time of the processor. So if we think about a machine which has a number of racks, a number of boards in it, and each of those boards are at different positions in that rack, and they may heat up at different rates, some of those processors may be running at a slower cycle time because of the power of the heat that's being generated in that device, and that may cause this clock jitter. And that clock jitter results in things not finishing at the same time, and synchronization being presented with a real problem. This is an example here of that issue. This is on Knight's Landing. This is a matrix multiply operation. We're looking at the power profile when we run that matrix multiply. At idle, it's running around 100 watts. We do the matrix multiply. The power requirements shoot up to some point, and then at some stage, the processor is heated. It gets heated up because of the floating point operations that are being performed, and the processor decides it has to turn down the power and adjust the frequency so that damage isn't done to the chip itself. So the thermal design point is reached, and the cycle time is reduced, and the power requirements go down, and my computation takes a little bit longer now to compute because of that adjustment that was made. It's out of my control. It's being done in the hardware. So that's going to present an issue in terms of this clock jitter, which may cause things to be affected in a way which was not anticipated, and synchronization causes issues there. So we end up with performance portability is something we all strive for. It's really the holy grail for high-performance computing. Standards help achieve that performance portability. There's a number of issues there, of course, with that. We need really to put in place some mechanisms that allow us to tune the code to the specifics of the hardware. And those tuning switches really can't be under user control. They're too complicated for a user to set, and they're very dynamic in terms of what's going on in the machine. So what we need to do is to have some auto-tuning framework in place that'll do it behind the scenes without the user having to be in direct control for that situation. And energy consumption, of course, is a big deal, and energy efficiency. I've already mentioned this business about performance. So I'm going to conclude here. This next set of bullet points here are things that I find exciting about the work that we're doing in terms of developing software. They're challenges that we have to look at and face and overcome in order to effectively write software in this exascale environment. So the one thing is about synchronization reducing. When I've got 10 million cores, I can't have a loop-driven parallelism. I can't have one loop launching 10 million things and then synchronizing at the end of that process. That would kill performance. Synchronization says we got one thread of execution running at the end of that. So I need to do something that would release more parallelism. And our architectures, our software architectures that we're designing are built in a way that makes them look a lot more like a data flow process. So data flow has been around for a long time, but we're starting to use those concepts in the design of our library software that allows us to express the computation in a way where it's not loop-driven, it's more of a data flow-like directed acyclic graph version of that algorithm to allow more parallelism to occur. We have to be in a position to reduce the communication. So communication is the thing which kills performance. It hinders the ability to really get at that high rates of execution. We want to be able to develop algorithms which have the minimum communication that can be derived or shown for a given algorithm, and then implement that, and hopefully we'll be in a better position to extract performance. We want to be able to use mixed precision. We want to be able to use 64-bit, 32-bit, and perhaps even 16-bit precision in the course of our applications. 32-bit is twice as fast as 64-bit on all hardware platforms. The floating point is twice as fast, plus you have half as much data to move, so you'll get a benefit from that. 16-bit even goes beyond that, being 4 times faster, and again, less data to move. So we want to be able to somehow approximate the solution using the lower precisions, and then when you're in the final stages of convergence, perhaps switch to the higher precision to maintain the accuracy. I already mentioned this business about auto-tuning being important, building it into the software to tune to the specifics of the dynamic environment that your software is running on, to adjust to it in a certain way to maximize the performance that we have. And another issue here is about fault resilience. When you have 10 million cores, things are going to fail. We have to design algorithms that can transition past failure, that is somehow recover from a failure and carry on. Perhaps approximate the data that's missing and carry on the computation in the presence of the failure. Or if you have a soft failure where a bit gets flipped someplace, you want to be able to detect and perhaps correct that failure and carry on the computation. And the final thing I'll just mention is this issue about reproducibility. So with reproducibility, some people insist on getting the same answer today and tomorrow if they run their application on the same machine today and tomorrow with the same data. So we have this notion that our computation would be exactly the same, but that's not the case. And it's not the case because I can't guarantee the order in which a collective operation will be done in a parallel computer. So if I run my application today and tomorrow with the same data on the same machine, I may get different ways in which the data is combined, and those differences may lead to round-off error differences, and those round-off errors could be magnified by ill conditioning in the problem or in the algorithm itself. And some people are insisting that this be done. You could do it, of course, but that would require a lot more of it may require more effort. So I think I'm going to stop there and ask if there are any further questions, or see if we can keep the power on a little bit longer.
Thank you. Thank you, Jack, and sorry again for this technical problem. So we have time for 2 or 3 questions. So.
Jack, just one point. In the one Nobel Prize on the timeline, they got much more than 0.3% peak performance, which is the CGG. How do you explain that they got 30 or 40% peak performance?
No, well, for that particular model, they did get higher than 0.3%. Yes, that's right. So it suggests that their application is driven not by sparse matrix computation, but by doing more dense kinds of computations. It
wasn't under the PDE, so
it was not a PDE. That's correct.
It was.
It was a PDE. I'm not sure the exact nature of that PDE and how it was actually implemented. I guess that's a better way to say that.
So I also had a question about HPCG.
Yes.
Your numbers look extremely bad. So how optimized are your codes?
Those are very optimized codes.
Because
believe it or not.
On Blue Gene,
yes,
we typically get like 30%.
And that's for an iterative method?
I'm sorry?
Is it for an iterative method?
Yes.
A sparse matrix problem?
CG.
Sorry, it's for CG?
Yeah.
Yeah. So you may have a different matrix structure than what we have. And our matrix...
Nearest neighbor.
Yeah. The ground rules say that you're allowed to optimize those things. So the vendors do take some care in optimizing it. I'm not sure exactly how much care was taken for the Blue Gene example, but in many cases they work very hard at that. I know NVIDIA does.
Because it is an example of a machine which has a very balanced CPU to communication, which you don't find.
That's right. So again, Blue Gene is a machine that was designed for scientific computing, and that was built into the hardware from the beginning. So it has a much better mix, as you say, for doing just that.
Also a question about HPCG. Nobody is going to solve it by a configuration method without reconditioning before we know that. And so why didn't you say, okay, here's a PDE, solve it as fast as you can? That would be better test, isn't it?
Right. So first off, the CG does have a preconditioner. So there is a preconditioner in the CG that we use.
Oh, okay.
So there is something there. In setting up the ground rules for the benchmark, you have to be very careful in what you allow and don't allow. Because, as you might guess, people will try to bend the rules if you're not very precise in how you state things. So we tried to be very precise. The CG method that we have does not go to convergence. It only does so many iterations, just an iteration, and we have to guarantee that they're actually implementing CG. So there's some rules about how that works, and there's some tests that are done on the implementation that the user provides for CG to ensure ensure that what they actually have is a valid CG. So it's complicated. We understand what needs to be addressed. You have to verify that they're getting the right answer as well. And how do you do that in the mix of this makes it more complicated than saying solve this PDE as fast as you can. So the ground rules have to be set up right in order for that to have a life beyond this. So anyway, we tried to do that. I guess that's all I'm trying to say.
The way the last one.
A question on what's driving now the evolution of hardware. Is it mostly HP or big data? And are these things necessarily contradictory, or should we be able to find a common ground?
Well, so let me confess my fear. My fear is that everything is being driven by big data, deep learning. And the hardware vendors are moving in that direction quite rapidly. And my concern is that they would abandon us because the money is over there. That is to say, they can make more money by developing hardware in that area. And this business about 64-bit arithmetic, they don't need that. So, my concern would be we would not even have that hardware accessible to us. We would have 32 and 16-bit floating point arithmetic, which would present a disaster from our scientific standpoint. So that's my fear. I don't know if that'll be realized. I hope not, but that's certainly a concern. With the DOE project, one of the things that DOE realized is that they have to incentivize vendors to develop hardware that's important for the DOE community. So they provide funding to the vendors so that they will focus on problems that are of interest to the Department of Energy. And again, with deep learning, with that being such a big area and such a large money maker for them, I guess I have a concern that things may shift. That's a good question.
Okay, thank you again, Jack. Thank you. I'm sorry again, Jack.